Wait 1 second. Good. So thank you all for coming. As Rak said, I want to talk about Kolmogorov-Arnold networks, which is some type of computational graph or a neural network architecture that we put forward together with mostly colleagues from IFI and appeared in this paper here last month. So the outline of my talk is as follows. I want to first start with an introduction to cans to explain what they are. In the second part of the talk, I want to talk about properties of cans and also contrast them a bit to traditional neural networks. And then in the third part, I want to talk about scientific applications of cans. And again, mostly contrast them with what has been done in neural networks. And in the end, I'll present a brief conclusion. Good, so let's start with Kolmogorov-Arnold networks. And to start this, I want to sort of start with actually with just standard multi-layer perceptrons or feed-forward neural networks, because these are a little bit more known to the community, and I want to briefly sort of just review them to make sure we're all on the same page and to make sure sort of you understand my notation, and then we can sort of compare them to what Kolmogorov-Arnold networks are doing differently. Good, so this multi-layer perceptron, what it is mathematically, it's a way to express a function, and the function is composed of the parameterized map from some input vector space, let's say R to the n here, some output vector space R to the m here. And the way this map is constructed is you compose different functions, and on the edges here, you apply affine maps, so meaning you take your input vector, you multiply it by some matrix W, and you add some vector B to it, and that then maps from R to the n to R to the P, where if W is an n by P matrix. And once you are in this vector space of R to the P, what you do is you apply typically unary nonlinear maps on these nodes. So after I've constructed this vector Wx plus B, I take its ith component and I apply some nonlinear function sigma. And if I don't do this, then I would just get a composition of affine maps, and affine maps close on the composition, meaning if I just take n affine maps without any nonlinearities in between, this would just be equivalent to a single affine map, and that would limit the expressivity of the model. So in the example here, we have a map from R squared into R, and this map is constructed by going into R to the 12 here first by multiplying by this matrix. Then I apply a piecewise nonlinearity, let's say a hyperbolic tangent. Then I'm mapping R12 into R3 here. Then I'm applying nonlinearity, I'm mapping R3 into R8, apply nonlinearity, and then I map it into R. And this this nested structure of alternating between affine functions and nonlinear functions, this looks it's a bit cumbersome, but there is actually a universal approximation theorem which goes back to Sebenko, and it tells you that if you make this neural network infinitely wide, if you allow for infinitely many parameters in your matrix, then you can express essentially any function you want. So there's no loss of generality to write your function in this way, essentially. And then, of course, the name of the game becomes, once you have this, becomes then to find these parameters inside the matrix W and inside this vector B, such that this function, which can be any function, is the function you want. So in the end, these neural networks, or most of the tasks we are facing and we are applying neural networks to, are just function fitting. In regression, of course, that's straightforward. Let's say you have a bunch of points, you want to find some function that sort of describes these points best. You can just fit a neural network to it. If you have a classification task, you need to find some decision boundary which separates cats from dogs, let's say. So you have to find a function here, some map that goes through your feature space and separates them into the different classes. If you have something like image generation from noise, you're doing some diffusion map from the noise into cat images. And if you have something like a natural language problem where you want to predict the next word. You need to find a function given sort of the words you've specified before or the words that came before. You have to predict the next word. So you're finding a map essentially from words to words. So this is why sort of neural networks are applied in all these areas. They just learn these functions. They can represent these functions. And for some reason, they learn these functions extremely well. So, but of course, neural networks are not the only way to fit functions. In fact, perhaps a simpler way of doing it, or on the face of it, simpler would be to just fit a polynomial to this function. So let's say you have a bunch of points, and now you want to find a polynomial that goes to these points. And if you have n+1 points, you can find a degree n polynomial. And this unique degree n polynomial will fit these n+1 points exactly, meaning a degree n polynomial has n+1 parameters, and I can use these n+1 parameters, I can adjust them. And by adjusting them, I can make sure that this degree n polynomial goes through all of these points with 0 loss. However, if I have degree n polynomial, I take a derivative, I also have, I get to a degree n-1 polynomial. And this has around, or I mean, if it was over complex numbers, it would have exactly n-1 zeros, meaning this function has n-1 extrema, or over the real numbers, it could be a few less. But it will have many extrema, so it will be highly oscillating between these points. So you see sort of between these 2 points, it goes up, then it goes down, it goes up, it goes down. So you have this extremely oscillating behavior. And this means that the generalization actually is extremely poor. So these points here were drawn, I drew these from essentially from a linear function with some noise on it. So the best fit to this thing would have been actually a linear function that goes something like this. It doesn't quite look linear because I plotted this on a log scale. And you can see this extreme oscillatory behavior. If I'm at 0, I'm in this case at 0.1. And then if I just go slightly away, my function jumps up to 10 to the 5. So of course, we don't have points in between, so we don't know what the actual value should be. Well, in this case, it was sampled from a line, but it's very unlikely that a good generalization is to move a tiny distance here in X space, and then the function all of a sudden jumps by 5 magnitude or 6 orders of magnitude. So this is what polynomial fitting gives you. And typically this leads to very, very poor generalization. So an alternative in the fitting community, this has been around for a very long time, is instead of trying to fit a single degree 10 polynomial, you can fit a bunch of piecewise polynomials. So in this case, let's say, and these are then called splines. So for the example of a cubic spline, this means I take a cubic function, ax cubed plus bx squared plus cx plus d, and this now has 4 parameters. And I put this between each of these points. I'm not trying to interpolate the entire thing with the degree 10 polynomial. I'm just interpolating piecewise polynomial between 2 points. And I have 4 parameters. I use 2 of these 4 parameters to make this function go through each of the 2 endpoints. And then I have 2 parameters left, and I use the last 2 parameters to make this function, the first derivative, continuous through these endpoints. So instead of sort of getting something that is ragged, I get something that looks more smoothly. And I'm just doing this for all pairs of points, and I get something that interpolates in this way. And now I don't have this huge oscillatory behavior. You see sort of this is more nicely behaved now between these different points. Of course, you don't need to use cubic splines. You can use higher polynomials here. If you go too high, you might run, again, the risk of getting this oscillatory behavior, but this is the idea of splines. You sort of, instead of fitting with one large degree polynomial, you fit with a bunch of piecewise defined smaller polynomials. And that is important later for Kant's. Good. So let's contrast this now with a neural network. So if I use a neural network, I can overfit. So I can run into this problem here that I'm essentially getting some oscillatory behavior, that my generalization error, meaning my error on unseen data is large, but this can be prevented. There are techniques around that actually mean that the neural network doesn't do this, or doesn't do this too strongly. And so what you can see on the left is I took the same points and I fitted a neural network to it, and I gave this neural network 1 million parameters. So now you might say, in this case here, I gave this thing, this was a degree 10 polynomial, so I gave it 11 parameters. And already these 11 parameters were too much, and I got this highly oscillatory behavior. So perhaps in this case, I should have fitted this. If I fitted with a polynomial, I probably should have fitted it with a degree 1 polynomial. As I said, this was sampled from a line in the end, or maybe a degree 2 polynomial here. So the fact that this was highly oscillatory was because I gave this thing too many parameters. Now, if you give too many parameters to a neural network, things start to work again for some reason. And this is what's called the double descent phenomenon. So if you look on the right here, what you see is essentially a plot of the complexity of the neural network, meaning in the number of its parameters, versus the error. And the blue one is the error on the training set, meaning sort of how far away you are from the blue points. And the green one is the error on the test set, on the unseen data. And in the beginning, sort of they both start to fall, and as I give more and more parameters to my neural network, they get better and better. I mean, here the error is big because the neural network is just not, or the fitting function is just not powerful enough to express all of the points that I need. But then eventually, sort of they start to diverge a little bit, and then the training error continues to go down as I start to fit these points better and better, but the test error goes back up. And this is exactly what we have seen here. So now you have a generalization gap where now I'm hitting all of these points exactly, but in between I'm making huge errors here. And this is called the bias variance trade-off, and this was known for a long time in the fitting community. What was perhaps only understood after neural networks were around is if you sort of still continue to go past it, so if this gets worse and worse and worse, and then at some point, this actually turns around and the generalization gap closes again, meaning the test error starts to go down again. So these neural networks overfit. And then at some point, if you give them, just continue to throw more parameters at them, at some point, they start to behave nicely again, and the test error starts to go down, and you can get even lower than this optimal point here. And that's what's called the double descent phenomenon. And that's together with the fact that if you give a neural network infinitely many parameters, you can represent any function. But this is the reason why we are seeing these gigantic neural networks with trillions of parameters in ChatGPT, for example. So because it's kind of difficult to ask the question of what this point even was. So this would require you to know essentially what's the intrinsic dimensionality of your data set. And in the case of language, that's a very difficult question. But if you just throw a sort of a gigantic neural network at it, it will, you don't have to find this point because you will be somewhere back here. Okay, so this is neural network theory. And now I want to contrast this with Kant's. So just let me just very briefly come back to this slide. So this was the computational graph for the neural network. Remember, we had affine maps on the edges and we had nonlinearities on the nodes. So now we take a Kant, and the Kant looks something like this. It's also in this case taken to be a map from R squared into R. But the setup is slightly different. So now instead of having linear maps or affine maps on the edges and nonlinear maps or unary maps on the nodes, we're doing more or less the opposite. Now we have unary functions on the edges, meaning I'm applying some function whose graph we are plotting here in the Kolmogorov-Arnold network. And on the nodes, we're just applying, we're essentially just summing up all the lines that come into this node. So now we have some linear map on the nodes and some nonlinear map on the edges. In the example here, we start with R to the 2. We apply these different functions, map this into R to the 3, and then we just sort of sum up the incoming functions here at this node. And then from R to the 3, we again sort of have edge functions that multiply this. And we go into R by, again, just summing them up in the end. And again, you might ask, why do you want to do this? Why do you want to write a function in this way? And there's a theorem due to Kolmogorov and Arnold. And it again tells you that you can express essentially any function in this way. So we have the universal approximation theorem for neural networks. And we have the Kolmogorov-Arnold theorem in this case. And either case tells us sort of you can, if you wanted to, you could write your function in this way. So that's already the basic idea. And I will explain sort of how we construct these functions. We do this using splines. That's why I introduced them before. But before we go there, I wanted to make a brief remark on the relation between neural networks and cons. So you can actually, I mean, since you can write a function in any function, both as a con and a neural network, it's sort of not too inconceivable that there's a map between these two. And I'm not proposing that anybody does this, but it might be useful for theoretical considerations because people have studied neural networks a lot and they have understood many things like this double descent. Well, double descent might not be fully understood, but at least it has been studied very well. And there are many proposals for how to explain this phenomenon. And there are many other things in neural networks like neural tangent kernels. There are many things have been worked out. And so it's just for theoretical considerations, the next two slides that I want to show you might be relevant. And also it might sort of help you to understand a little bit of what is going on. So in essence,
Fabian, there is a question in the audience.
Was there a question?
Yes. If you want to ask, please ask by turning on the microphone. So if there's any question in the audience, please raise your hands. Is there a question?
Yes, I have a quick question. So as you know, Kolmogorov and Arnold are famous for their work in chaos and dynamical systems and so on. So I'm sure, building up the network was not exactly in the back of their minds when they proved this.
Yes.
So can you tell us a little bit about the motivation for them to work out this theorem in the first place?
Oh, you mean their motivation?
Yeah. I mean, what was the context where this theorem came up?
That's a good question. Unfortunately, I'm not familiar with the history. I apologize. So I mean, it's a result in analysis, but I can't tell you what was sort of their original motivation to prove this. I'm not familiar with the history,
Okay.
unfortunately.
One more question.
Okay. Yes.
Now, can you hear me?
Yes.
So this CAN network is kind of a dual of the FNN. So do we have a finite set of these activation functions that we choose, or is it an infinite set of functions?
Good. Yeah. So in the end, if you want to represent, I mean, yeah, just like the universal approximation theorem tells you, you need an infinitely wide neural network and a nonlinear activation, a non-polynomial activation function. The Kolmogorov-Arnold network essentially also requires you to have sort of, yeah, in the end, going essentially from Kolmogorov and Arnold proved this in the context of going essentially just of having just one layer essentially. So the Kolmogorov-Arnold theorem tells you that you can go from essentially into R by taking different functions and sort of taking the input, pumping it to many different functions and summing them back up. And so essentially this step here would be something that Kolmogorov and Arnold tell you, you can construct this map by going, you can construct this map by representing it as this computational graph. And in the end, if you make this fine enough, you can represent any function. And what we now did is essentially we took this realization and we defined what we call then the Kahn layer. So going from here to here, and then we just started stacking these different Kahn layers. So essentially Kolmogorov-Arnold was just a one-layer Kahn or two-layer Kahn. And we just sort of took this and started stacking this higher and higher to make, if you want, a deep Kolmogorov-Arnold representation.
Yeah, I think you can continue with your talk and then we can ask more questions a bit later.
Okay, good. So yeah, as I said, we can relate this to neural networks, and I'm not proposing that you do this in practice, but in theory, it might perhaps be useful. And essentially the way this goes is you take these functions here, which as I said, in our case, are just taken to be piecewise polynomials or splines. And you could, if you were to replace these by a small neural network that just goes from R to R in an intermediate layer, all of them you would have, again, just a standard neural network. Or put differently, let's say you have a neural network, you can make it non-fully connected. You skip every other layer and you reproduce a Kahn from it. So let's say you have have this neural network. In the end, they both describe maps from R squared into R here. And so let's say I take an intermediate step, I take R to the 3 here. And now I sparsify my neural network, meaning I'm throwing away all of these connections here. Now it looks something like this. And now this starts to begin to take the structure of a Kahn. If I now focus, for example, on this map from R to R here via these 3 hidden layers, or this map from R to R by these 3 hidden layers, and so on, and I summarize this now, or I take this to express this graph, I now precisely get this Kolmogorov-Arnold network. So in this sense, sort of, I can think of Kolmogorov-Arnold networks as just being very sparsified neural networks. So in principle, you could have said the neural network can learn the same thing as the Kolmogorov-Arnold network. It could have just learned to sparsify itself in this way if this is very beneficial. But of course, the loss landscape of these neural networks is very, very complicated. And this is most likely not what a neural network learns. So, but it's a theoretical way of connecting sort of what a Kahn does and what a neural network is doing. Yeah, so in a Kahn, as I said, Kolmogorov-Arnold representation theorem, essentially, if you use a continuous unary function, you can represent any function. What we propose in the paper is to use a function which is composed of 2 components. One is a spline, and one is some quote-unquote biases function or some bias function here that we add to the spline. And we take sort of this sum and we multiply it by an overall weight W. So this is a overparameterization of the problem. Of course, we could have just absorbed this W into the function B and into spline, but we found this representation here useful. So W is in essence is a learnable weight, and it's measuring the overall magnitude on each edge. So it's telling you essentially how big this function is, how big sort of the contribution from this node into that node is along this edge. For B of X, well, we can choose essentially any function. What we chose was the CELO function. The CELO function is like almost like the ReLU function. It's like a continuous version of the ReLU function here. It's defined to be x over 1 plus e to the minus x. And for the splines, we use so-called B-splines. So what these are is essentially I have a bunch of spline functions here. the blue one, the green one, the yellow one. And then I'm just multiplying them with some learnable parameters CI here. So these are my training parameters. And then I'm summing them all up. So I get sort of some function from here by taking these splines here, which have some compact support on a finite interval and are 0 outside. I multiply them with some constants, meaning I'm lifting them up or down. And then by summing them all up, by superimposing them, I'm constructing this spline function. And I take this then and I add it to the CELO. I multiply this with an overall weight. And this is what I'm doing at each edge. So this is how I build my edge functions. And then, as I said, at the nodes of the graph, I'm just summing up all of these contributions. For the initialization, what we do is we take these learnable parameters CI in front of the B-splines, and we are drawing them just from some Gaussian with zero mean and some small variance. And the reason why we do this is we want to initialize the network such that essentially each spline function or each edge function is close to 0. And the W's we are initializing just as we would initialize a standard weights in a neural network. So in this case, we chose Xavier initialization, which is also just sort of populating them from some random distribution. And for the B-splines, we use a grid here in the beginning, which is not completely uniformly spaced as drawn here, but it has sort of 5 grid points. So we have these splines in between, and then you can construct some sort of function approximation in the spaces. And typically we use cubic splines. We have cubic splines at these 5 interval points, and then by multiplying it with these CIs, we're generating the different edge functions. Good. So that's a setup, and then you just start to adjust with some optimizer the coefficients CI in your splines and the coefficients W that multiply the overall size of each edge. And now during training, what could happen is that if you have a spline, of course, it's just defined, let's say, between here and there. So it could be that as you train the neural network, the input to some of the nodes that then go into the edge and I need to apply the spline to fall outside of this region. So what this means is then we have to somehow extend the grid here. We have to add more basis functions such that we can deal with this new input. I mean, this is, if you want, this is a disadvantage of splines. If I had a neural network, I can just sort of throw any real number at it and will produce an output. So if this neural network was never trained with this, the output might be very, very bad. This is what's called an out-of-sample input, giving it something that it hasn't seen before at all. I mean, something that's not in the distribution with which it was trained, but at least it would give you something. For the splines, if I have sort of just the basis functions between, let's say, -1 and 1, and now all of a sudden, after training, this sort of gets a 2 as an input, I need to somehow extend my grid. And the way we do this grid extension is we essentially add new basis functions, and then we find the coefficients in front of this new set of basis functions, such that on the part where it has been trained, it's closely resembling the function that it has learned, but now sort of it also has some value outside of the function's initial domain. So now I can evaluate this there and use or continue training where now this edge function will also return something outside of this interval. Also, you might want to just sort of refine your grid at some point to get a higher accuracy. If you just have 5, of course, if you just have 5 grid points, if you just have 5 basic spline functions, I cannot reproduce any function by just summing up 5 cubics. So we also have the possibility to make this finer, to add more basis functions without extending this interval. And if you do this, again, so we do this extension such that we reproduce the function that we have learned so far. So these are two things that you might have to do during training. Of course, you could have tried other things. You could have just done some sort of normalization such that after each layer, or meaning after summing them all up, you map them back into this interval -1, 1. This is sometimes also done in neural networks, some sort of better layer normalizations. But in this case, we found that extending the grid actually works better than just normalizing after each node, after each sum. Good. So this is just the basic setup of cons. Let me just briefly recap. So we have nonlinear activations at edges and linear functions on nodes. The edges are learned from B-splines, meaning we have a set of basis functions with compact support, and we just add them together, multiply them by some learnable parameter Ci. We add a sealer to it and multiply the whole thing by W, and map it in this way layer by layer into Rs, and then at the nodes we sum them all up, and in this way we represent our function. And then in order to train this neural net, well, these cons, what we do is we just use some optimizer to adjust these parameters C in the B-splines and the parameters W to make the function go through, I mean, yeah, to make the function represent the function we want. Good. So this is essentially about the end of the second part where I explain how cons are set up and trained. So now we know that we have these things, we are studying the properties of them. So one thing we wanted is, in the context of, at least in the scientific context, we wanted them to be more interpretable than neural networks. And they already have a good chance of being more interpretable because, as I said in the beginning, if you train a neural network, typically you just throw as many parameters at it as you possibly can, and then you're in the double descent region and your generalization error goes down. But if we look back, let me quickly go back. If you look back at this here, this is essentially what the cubic spline learned. And the cubic spline has, for each point here, as I said, between each interval, it has 4 parameters. So this thing has then maybe something like 40 parameters. It looks like this. This thing here has 1 million parameters and looks almost the same. So in some sense, this looks extremely wasteful. You're using all of these parameters to reproduce something that you actually can reproduce with much, much fewer parameters. So the hope would be then that if you prevent overfitting, also with or if you get high accuracy also with much fewer parameters, you have a better chance at interpreting it. Also, the way we sort of visualize the cons in the end also makes it easier to interpret them because it's more localized, it's more clear what each part is doing, and we will see examples of what I mean exactly by this later. But in order to make it sort of to reduce its complexity so that humans can look at it and understand it better, we want to do more steps which have to do with sparsification of the con. And for that, sort of we again took inspiration from what people in the neural network community do to achieve sparsification. And what they do is essentially they add an L1 rate regularization. So meaning you're not optimizing your actual loss that you're interested in minimizing, but you take your loss and you add to it a sum over all parameters in the neural network. So you're just taking the absolute value, you're summing them all up, and then we have some parameter lambda in front that controls the relative size of this weight regularization and the loss. So what this now means is the neural network will try to make the loss as small as possible without making the weights large. So if it can, it will keep the weights small and still sort of optimize here. The optimal will be small weights and small loss in this case. And the reason why you use L1 loss and not, for example, L2 loss for sparsification is, let's say this is your loss here. This is the piece from L. This is the piece from the weight regularization. If you use an L1 norms of the equidistant lines from this square here, and if you now intersect this here, the intersection is very likely to lie along some of the parameters being 0. Whereas if you used an L2 norm or so, then the intersection would likely be away from, I mean, the optimum would be not on one of the axes, meaning not one of the parameters would be set to 0. So this is a sort of an intuitive understanding for why the L1 weight regularization tends to lead to sparsification and set some of the status, some of the parameters to be exactly 0. So we wanted to do the same thing. We had to find a way of sort of, in some sense, define the L1 norm for the Khan. And so what we did is we defined essentially something very similar to the sum of the weights absolute value. We defined this to be the sum over all the inputs of the edge function. So I take this, I take my edge function sigma here, and then I'm sort of taking all of the inputs, I sum them all up, and that's what I define to be sigma here. And then for Khan layer, I'm just defining the L1 norm to be the sum of these L1 norms. So if I have some node, I have some incoming things, I have some outgoing things, and I'm summing up all of the incoming edges, sort of the norm of all of the incoming edges and all of the outgoing edges. So this is what I call this absolute value of phi here. And this is what I add to my loss. And this by itself already will lead to some sparsification, but we wanted to achieve even more sparsification. So we also add a second piece, which is called entropy regularizer. So I'm calculating the entropy as a p log p, where these p's are essentially here this value of sigma ij divided by the total sum of all sigma ij. So I have these pij's here, which are defined to be sort of just the activation function between sort of nodes I and j. And I'm dividing this by the total norm, I mean, by the absolute value here, and then I'm just summing this p log p. This looks like an entropy. And then I'm adding this piece and this piece to my loss. So my total loss is essentially the target function that I actually want to optimize, plus some parameter lambda, which is controlling the overall size. And then I have this phi for each layer, and I have this entropy for each layer, and I'm also adding two hyperparameters mu1 and mu2, which allow you to sort of dial the relative size of these two, and lambda controls the overall contribution of the sparsification. So if you make lambda bigger and bigger, the more you're drowning out your actual target function over just having a very, very simple neural network where the activations are all small. Good. So this is how we sparsify, and once we have sparsified, we can prune our neural network. So the way we do this is we prune them at the node level, and for this we define an incoming score and an outgoing score, and for this we just take this to be the maximum that any of these incoming or any of these outgoing edge functions can take, and then we decide to prune a node if either the incoming or the outgoing score drops below a certain threshold. If the maximum of all incoming is very small, I probably can forget it. And if it's not doing anything else to the rest of the network because all of the outgoings are very small, I can probably also drop it. So we prune then based on these maxima. And in the Khan, we visualize how important the incoming or the outgoing edges are by just fading them out, and we sort of give them a transparency proportional to this tanh function. So this will make it transparent if the activation is very, very small. Finally, we also allow to freeze some of the edge functions to some user-specified function. This is, again, sort of if you want to use this for scientific discovery or for some symbolic regression or so, you can look at what these splines look like. And perhaps you have then a conjecture, this looks like a sine, or this looks like an exponential or a log or whatever. So you can just say, okay, so I believe, or maybe I'm a domain expert and I know that this has to be the log of something. So then I can fix my function at some point to be, let's say, a log or a sine or whatever, and just train the rest of the functions. And in this way, you can sort of zero in on the function that the Khan is actually expressing. So let me give an example of this process here. So let's say we want to learn the exponential of sine pi x plus y squared. What you do is you just sort of initialize your neural network, then you train it, and then, as I said, sort of we start to fade out the different connections here based on how strong they are activated. And in the end, you would see a graph like this, where most of them have been faded out, but you see sort of this x here is activated with something that looks like a sine here. This y here is activated with something that looks like a parabola, so something that looks like squared. So at this node, it looks like I'm getting a sine of x plus y squared or something like this. And then at this point now I can just prune away all of these. So I can essentially just focus or zoom in on this part of the network that looks like this. And if I look at this function, this looks something like an exponential. So now let's say I'm rather confident that this is a sine. I can fix this to be a sine function here, not to be this cubic spline that the Khan learned, but I just sort of by hand say this is a sine now. And this is a parabola, so this is x squared. And this is an exponential, so I can just fit it to this. I continue sort of finding the precise pieces of the sine, this square and this exponential. And in the end of the Khan would output 1.0 e to the 1.0 y squared plus 1.0 sine of 3.14x. So it has essentially now learned the coefficients of these functions here. This was done in the last step where I sort of just find the coefficients here in front. So this is a way of sort of doing symbolic regression with Khans. And this is made possible because there are, in contrast to a neural network, there are very, very few edges, and you can sort of see what the edges are doing, what type of function they are learning. Here's another example. So this is a video. Sometimes these videos are a bit choppy over Zoom, so I apologize if it's not very smooth for you, but I'll play it anyways. So what we are trying to do here is we are trying to learn this function, the exponential of sine of x1 squared plus x2 squared plus the sine of x3 squared plus x4 squared. So let me play it, and I hope it's coming through somewhat okay. So you can see as it is being trained, I start to fade out the connections that don't matter too much. And for the other ones, the Khan is quickly locking in on some functions. I'll pause it here. So you see, again, I have learned some square function here and here and here and here. So I'm taking my x1, x2, x3, and x4. I'm applying a parabola to it, so I'm squaring it. And then at this node, I'm just summing up. So this node doesn't have x3 and x4 enter anymore. I've pruned them away. Not only x1 and x2 enter, and I'm sort of squared them, so I'm summing them up. The same at this node, I'm summing up x3 squared plus x4 squared. Then I have something that looks like a sine, so I take the sine of the sum, I take the sine of this sum, and then I sum up the sines at this node. And then finally, I'm applying the exponential, and where I'm summing up the single exponential. So this is how I'm reproducing this function from training. Good. So the next property I want to discuss are neural scaling laws for Khan. So what we mean by neural scaling laws is we study how the test error behaves as a function of, typically people study 3 axes, the number of parameters of your neural network, the training time of your neural network, or the size of the training data set for your neural network. And you see that essentially the error goes down like a power law n to the minus alpha if you optimize along one of these axes. If you make a neural network bigger, you train it longer, or if you give it more training points, typically you find this power law scaling, and people have sort of put forward several models to try to explain this exponent alpha here. So one of the explanations is or predictions of how this should scale is by Kaplan and Chara, and what they suggested is that this alpha is linked to the intrinsic dimensionality of the input manifold, meaning any data, be it sort of cats and dog pictures, be it, let's say, just coordinates on an XY plane or language, there's an intrinsic dimensionality to this data set. And it this scaling parameter alpha here will be proportional to 1 over this intrinsic dimension, and it will be proportional to k, where k is the degree of a degree k piecewise polynomial that I'm fitting. So if I'm using a Ruehle, remember Ruehle is sort of a piecewise function which is either 0 or the identity. So I would be essentially fitting a line. K would be 1, and this means that alpha would be 2 over d, where d is this intrinsic dimensionality, which might be hard to calculate in practice, but of course for some examples you can just construct examples where you know d, and then you can compare against this. So let's say if you have a function, just a mathematical function which has inputs, 100 inputs or so, and these inputs are all independent, the intrinsic dimensionality would be 100, and your alpha would be very, very small. So your improvement as you scale up the number of parameters is very, very poor because the exponent is very close to 0. That's essentially what the curse of dimensionality is telling you. If you have a large dimensional input, your improvement is very, very small. If you compare this to Kahn's, if we have a piecewise polynomial of degree k, theoretically we get a scaling of just alpha just goes with k plus 1, and d does not enter in our case. So the intrinsic dimensionality of your data doesn't matter. You always get a k plus 1 scaling. So on the theoretical grounds, and we explain this in the paper, so you would expect this scaling, and this has a huge advantage over this scaling because it does not suffer from the curse of dimensionality here. So if you use cubic splines, this k is 3, so we expect alpha to be 4. And now we just ran some experiments. If we just take, in this case, we just took the function. The Bessel function has a single input x. So we can fit it essentially with just one cubic spline from R to R. And this can be represented by a 1-1 Kahn. So it's one input to one output. I'm just putting a cubic spline in between. And if we now train the Kahn and compare it to several NLPs, you see sort of the theoretical scaling for the Kahn would be n to the minus 4 if we use cubic splines, because that's k plus 1. The theoretical scaling for the neural network, according to Kaplan and Chalmers, is also n to the 4 if I use or n to the minus 4, because the intrinsic dimensionality in this case is just 1. So if I compare these two and I look at MLPs here for different depths, 2, 3, 4, 5, I see sort of initially they follow this, but then they sort of tend to flatten out with the number of parameters. Whereas for the Kahn, I'm seeing this theoretically predicted n to the minus 4 loss over large distances here in the number of parameter space. So now my loss is already much smaller than what we achieved with an MLP. As a second example, we can take something that has an intrinsic dimensionality of 2 here, because I just have independent x and y. This is the function that we looked at previously, e to the sine pi x plus y squared. So again, so for the neural networks, we would expect this n to the minus 2 scaling, which is followed here, and then at some point it flattens out. For the Kahn, we would expect this n to the minus 4 scaling again, because it's again just a cubic spline, and you see again this is followed over some range of parameters here rather nicely. And again, this improves sort of this, I mean, it will flatten out, but it's flattening out later, meaning at much smaller loss than the different layer and MLPs are. And finally, a more extreme example, so where we just have 100 input parameters, and I'm just summing them all up here. So now the theoretical scaling for the neural network, because of the curse of dimensionality, 0.04. So this is almost flat here. And we see this in practice here. For the Kahn, it should still be n to the minus 4. And well, it's following this a little bit, but then it's also dying out here. So this is about neural scaling laws. And you see, so with much fewer numbers of parameters, we can already achieve a much smaller loss, which is due to the Khan's not suffering from this curse of dimensionality of flattening out so quickly. Another thing which at least used to be a problem with very, very big neural networks, this behavior is not so clear anymore, but it's something that was stopped catastrophic forgetting. So if you have a small neural network, and let's say you just train it with this data, the Khan locally just fits essentially some spline to this region. So you get this, and then outside you just get some noise from the initialization. Your MLP, if you just support it, if you just supply it function values here, it will look like this, and then outside of the domain in which it was trained, it just has some generalization error and goes up like this. Then I train it for a while with just sort of input from here. The Khan just learns, since it's this locally defined thing, it just learns this. The neural network learns to predict this peak now, but it forgets what it had learned here. And outside of things it has ever seen, it's just doing whatever. And then you continue sort of giving this, and the Khan sort of step by step just adjusts its local splines to match this different data, whereas the neural network is forgetting what it had learned before and is just doing something different. And the reason is that neural networks sort of don't have this locality property that Khans have. So if I just have all these parameters going into some node, and I now have to adjust the output value at some other point, I'm just adjusting some of the input values, and there's no locality to this. Sort of my output is calculated by summing up all of these different things with this highly connected neural network. And this means I cannot sort of just locally adjust the value that the neural network learns here without changing what it does there. Good. So these are the different properties of Khans I wanted to discuss. And in the last 5 minutes or so, I want to show you or two examples of a scientific application for Khans. One is using them to solve partial differential equations. And there we just studied a simple example of a boundary value problem. So we took the 2D Poisson equation here, which is sort of the double derivative of x plus the double derivative of y is equal to some function f on a domain. And for f, we chose this function. And the reason why we chose this complicated function is because in this case, the solution looks very nice. In this case, the solution is just a product of signs. And the way you sort of use neural networks to solve PDEs is you let the neural network be the function u that solves this PDE. You use this PDA itself as a loss function, and then you just adjust the parameters in this neural network until this equation solves. So my loss function is just uxx. So I take the neural network, I take two x derivatives, I take my neural network, I take two y derivatives, I subtract f, and I take the absolute value of this, let's say, as my loss function here. And the loss will be 0 if and only if my neural network solves this differential equation. And then I also have, in this case, so there's an elliptic equation. So I need closed boundary conditions. And I'm just using on the entire sort of boundary of my domain on which I want to solve this differential equation. I'm just setting u equals to 0. So I then also have to sample some points on the boundary, and I just impose that my function is 0. So my loss will just be, in this case, u squared. And of course, this will be 0 if and only if u is 0 and all boundary points. And all interior points, it has to satisfy this equation. And then again, we train this and we compare it to different MLPs. So here we have a Khan, which has two inputs, the x and the y coordinate. Then it lifts it to r to the 10. And then it's just summing it up to r. And this is then what this function u is. And if you compare these two lines, the orange line is sort of an MLP with exactly the same structure. And you see, so this is the loss we get compared to the Khan, which has this loss. And if you wanted to resample this, you would need an MLP with many, many more parameters. In this case, sort of the green line is an MLP with 2 into 100, so R2 into R100 into R100 into R100 into R. So now I have 3 hidden layers with 100 nodes each. And then I start to sort of get in this region at least something that is similar to behaving to the Khan. And again, we can look at the scaling with the number of parameters. So we find them this scaling for cons, and then the MLPs start to flatten out. And we again compare this to this theoretical value of n to the 4 for cubic cons. So this is for solving a partial differential equation. The second thing I wanted to discuss is an example where we applied this to data, to scientific data and knot theory. Let me skip this. So for knots, essentially what a knot is it's a tangled up circle. And the task is then to sort of classify these different knots. And we want them we want this knot to be the same as this knot. So if I put a dent in here, or even if I twist it, I want to call all of these knots to be the same. But then there are knots that are genuinely different that I cannot sort of just smoothly deform into, let's say, this knot. I would have to break this. I would have to cut it and pull this, let's say, this past here. If I don't do this, I cannot translate these two knots into one another, and they are genuinely distinct. So mathematicians then are interested in describing somehow these knots by characterizing them using invariants that sort of will not be sensitive to me doing this to the knot or doing this to the knot. But I want sort of these invariants to be different for this and this, but I want them to be the same for this and that. And the way they do this is they sort of have some geometric invariants where they actually look at these knots and at them as geometric objects and assign geometric quantities of, let's say, lengths of geodesic curves in these knots, or they take the knot, they drill it out, so they drill out the knot from the three-dimensional space and calculate the volume. So there are these sort of geometric invariants that you can use to describe a knot. There are also topological invariants. So you can, for example, assign a polynomial to a knot. You can assign vectors to knots. You can assign real numbers to knots, and they are constructed in a way such that sort of you get the same number no matter what the knot looks like, but then you get different numbers here. And these are very, very different ways of thinking about knots. And it begs the question whether these are related and how. And sort of more generally, the question you're asking is, you're given in a mathematical data set, you're just given a collection of data, and you're asking, is there a relation between these data? So essentially, we want to find some functions f and g, such that if I take f and I apply to some of the data, it equals some other function g applied to some other subset of the data. Or if I was to bring g on the other side, I could write this as f minus g is equal to 0, and I call this the capital function f. And this is a problem that DeepMind did in the context of knot invariance. So they studied precisely the relation between geometric and topological knot invariance. So I could feed in some geometric data here and see whether I can sort of produce the same output from feeding in some topological data there. So if you wanted to do this in general, or if you wanted to sort of brute force this problem, what you would have to do is you would have to take the power set of all inputs, because you don't know so which inputs together determine a certain output. And then you would have to train a neural network. So let's say you just give it x1, and then you just give it x2, and then you give it x1, x2, and so on, and you try to produce some of the other features. So the power set has 2 to the n combinations. So doing this in general becomes not feasible if you have many knot invariants, let's say. So we don't do this. Instead, what we do is we turn this into a supervised machine learning problem, where we say we want to learn a function g of x such that it is 1 if x is not data that belongs to a knot, and it's 0 if it's not data that does not belong to an actual knot. So what I mean by this is we take the data that DeepMind prepared took from a knot theory database, and we corrupt some of the features. So we take sort of this collection of all knot invariants for one of the knots, all these knot invariants for the other knot, and now we produce fault samples by just permuting, let's say, the entries in the first row. So this might be, let's say, the volume, and then I'm just switching the volume, but I'm keeping everything else. So now I have a new vector where I have just randomly permuted these things, and this does not correspond to a knot most likely anymore. And then I'm just training this function to be 0 if it corresponds to a knot, and 1 if it doesn't correspond to a knot. This helps with sort of avoiding to just learn the trivial function. Of course, if I was to just trying to learn this function capital F, the neural network might just learn the function 0 everywhere. This solves this problem, but I haven't learned anything. This F, I want this to be a non-trivial relation between these different inputs. So doing it this way will ensure that I can learn something non-trivial, and then I can relate this back to the original function F that I've tried to learn by pumping it through a very narrow Gaussian, because this G will be 1. If I take a Gaussian that's centered around 1, I know that f of x is 0 if this sigma of f of x is close to 1. And this means then that g of x is a good predictor, because it will be close to 1 if f of x is 0, and it will be close to 0 if f of x is not equal to 0. And then we did this for different not theoretic data, and we discovered in this data set essentially a relation that was discovered by DeepMind, also using their way of finding knots. But in this case, so you can just look at the Kan and you see the quantities that enter in the end. We also found a trivial relation among this data, which is essentially just a definition. But you, again, so due to the sparsification and pruning, you can just look at this and you see in this example here that these 3 things enter together into the final quantity. And as I said, in this case, it's just this definition of cusp volume, which is the product of the longitudinal and the meridional translation. But if you look at what the cusp did, you can actually interpret this. So what it does is it takes the longitudinal translation here, and it somehow needs to multiply it. So what it does is it learns a log here, and it learns a log here, and then it adds these 2 logs up, and it learns a negative log here. So it takes a negative log of the cusp volume, plus the positive, plus the log of the longitudinal translation, plus the log of the meridional translation. And then if I take the exponent, if I apply my logarithmic laws, I will just sort of get the product here of the sum of the logs is the product of the arguments, and then I take the log, and then I get minus the log of the volume. So if I rearrange this equation, I precisely get the cusp volume is equal to the longitudinal times the meridional translation. So I can essentially, in this case, I can even read off the precise correlation between this data. So this is all I wanted to say about Kans. If you want to try them out, we have a GitHub repo where you can download it and just play with it yourself. There are Jupyter notebooks that sort of introduce the idea for some data sets, so you can just sort of start playing with them. So to conclude, we discussed Kans as an alternative to neural networks, where the nonlinearities are splines sitting at edges and the nodes are linear functions. We discussed how to sparsify, prune, and visualize them so that they are more interpretable, and sort of argued that they are extremely sparse neural networks in some sense. They work with much fewer parameters, and they exhibit better scaling laws than neural networks. And sort of the piecewise nature in which they are defined, you don't suffer from catastrophic forgetting. And then in the end, I discussed them sort of how to apply them in the scientific context. We saw that they work very well on PDEs. They also work very well on other mathematical and physical data. I didn't discuss this, but it's in the paper. So we sort of looked at special functions at the Feynman data set and so on. And lastly, I showed an idea how you can use them for scientific discovery of previously unknown correlations in some mathematical data set. In this case, it was knot theory. And this will allow you, hopefully, due to the visual and interpretable nature, to find new relations among your data. And with this, I want to stop. Thank you very much.